This is an example of an AC analysis problem at level 2. So we'll go into AC analysis. And as I mentioned before, this covers things such as voltage and current division, and superposition, and various other topics that are not part of nodal and mesh analysis. So let's look for problem type 1 here, and we'll first show an example of that. As always, we have examples and exercises at the same levels of difficulty. So the first thing we notice about this problem is that it's being given to us actually in the time domain, unlike many of the other problems that are given to us in the phasor domain. And we know that because we see, for example, the voltage source is a function of time here. It's a cosine function rather than being a complex number, which would indicate it's a phasor. Also, the reactive element values are in farads and henries, which again indicates time domain, whereas they would be in ohms in the phasor domain. So the first task here is it's actually converted from the time domain to the phasor domain. Now the impedances are all in ohms, and we have a phasor value for the voltage source, which is a complex number indicated here in polar form. And the conversion here is similar to what we did in the impedance simplification game, so that's outlined here. Now, this is neither single loop nor single node pair, but we notice that if we combine these two impedances in series, which you can do once we're in the phasor domain, unlike the time domain where you couldn't combine a farad with an ohm, for example, now because they're both ohms, we can combine them in series, and that's being done here. The impedance is simply added in series, and it's represented now by a general impedance. A rectangular box for a fully complex impedance is the symbol that is used for that. And having done that, then we can combine this impedance and the inductive impedance in parallel. Even though there's a sought voltage, that voltage will not be affected by combining those two elements in parallel, and that will make it into a single loop circuit, which is amenable to a voltage division formula. So after combining that, we have this J6 is replaced now by element Z2, and to compute that combined impedance, we remember that combining impedances in parallel means we have to take the reciprocal of the sum of the reciprocals of each individual impedance. We have the J6 and we have the 5 minus J 2.5 ohms. And evaluating that on a calculator, or if you like, you could use the product over some formula since it's only two elements. But really for a calculator, this is probably easier. That gives us the combined impedance here, which is a fully complex number. And so again, that's represented by a rectangular box. And at that point, then we're down to a single loop circuit, which means since we have a voltage source, this is simply a voltage divider where part of the voltage will drop across Z2 and the other part across the 9 ohms. And so we use the standard voltage divider formula as shown here. So we have the source voltage here, the one angle 0 degrees. And then we have the impedance of interest on which the sought voltage is present in the numerator. And then we have the sum of that impedance and the 9 ohm impedance in the denominator. So remember that the voltage source divided by all of the impedances added together will give us the current in this loop, and multiplying that current then times the impedance of interest will give us the voltage across that impedance of interest. We do, however, as always, have to pay close attention to the polarity, and so we notice that the positive side of the voltage source is connected to the positive side of the sought voltage, and its negative side is connected through the 9 ohm to the negative side of the sought voltage. Therefore, they have the same sense, and there's no need, therefore, for a minus sign in front of here, which there would be if, for example, the plus and minus were reversed here, or this plus and minus were reversed. In either of those two cases, we would need a minus sign here to correct for the polarity. So now we have this expression, and we just evaluate that directly on a calculator, which I'll illustrate in the problem, and that would give you this value in polar form. And then we have to do an inverse phasor transform to put that into the time domain. Notice there's no time here, so that's in the phasor domain. And that transforms into a cosine function. We have to use the angular time frequency, which is given in the problem, which is 20 kiloradians per second, or 20,000 radians per second. So I've just put 20,000 here for simplicity. It doesn't show the radians per second, but that is the unit. And then the magnitude of that is just the magnitude of the phasor, the 0.39, and then the phase angle here becomes the phase angle added in the cosine. And then as the phasor has units of volts, this voltage as a function of time in the time domain also has units of volts. So that would be the final answer. So that illustrates this problem. Now let's work a problem of that type. Again, we're on the medium or level 2. So our first task is to convert from the time domain into the phasor domain. And we know that we're in the time domain here because, again, the voltage is given as a function of time. Notice the t, of course. And also the impedances are given, or the reactive element values, rather, are given directly in henries and farads, which are not impedances, and therefore this is the time domain. So what we want to do is to convert those into impedances down here. So and this process, of course, is very similar to what we did in the impedance simplification game, except that we now also have to do a phasor transform on the voltage source, which we did not do in that game. So that's very simple because we have 4 cosine 90t, and notice that's plus 0 degrees basically because there's no additional term there. So that means that the amplitude here will just be a 4, and then the phase angle will be 0. And remember that the 90, which is the omega, is not used in the phasor value, so that will not appear here. Next, we have to convert the 80 millihenries into the appropriate impedance, remembering that this is at a frequency of 90 radians per second. So to do that, we're going to need a calculator. So I'll illustrate this here on a TI-8384 emulator. And we need to remember that, first of all, we want to make sure that we are in the complex number mode. So here it's actually in the polar mode right now. If it said real, that would not work at all. But I want it actually in the rectangular mode for right now because impedances need to be expressed as rectangular numbers. So I'm going to go and change that mode. So I'm going to go down here. And by default, you'd be in the real mode, but I'm going to go in the rectangular mode. So I click enter there. And the angle mode doesn't really matter since I'm going to be using rectangular mode, but I'm in degree mode right now. Okay, and we see that, we can verify that always at the top of the calculator display up here. Okay, so now we need to find the impedance of the inductor, and you have to remember that the impedance of an inductor is j omega L. So on the calculator, j is written as I, using the mathematician notation. I times omega, which is the 90. And of course, we don't multiply that by 2 pi because that's already omega. It's not the cycle frequency, or f. So that's then multiplied by the value of the inductance, which is the 80 millihenries. So we can write that as 80 e to the negative 3, or I could have written it as 0.08 also, would also work. And so that gives me 7.2i is the value. So I'll go ahead and enter that here. Except now I'm going to use a j rather than an I because that's the notation we use in electrical engineering to avoid confusing I with current. Okay, so now for the capacitor, I will need to remember that the impedance of a capacitor is 1 over j omega c, or if you like, negative j over omega c. So let's just write it that way, I guess. Let's go minus I. Remember, I is on the decimal point button at the bottom. Now divided by omega, so that would be divided by the 90 radians per second. And then we also need to divide by the c, which is 1 millifarad. So let's just enter that as 0.001 here to make it simple. Okay, so that's negative 11.11 I. And so we'll enter that here as negative j 11.11 ohms. And now we should be done converting to the phasor domain. So I'll click this button here. I'll enlarge this first. And it tells us that that's correct. So now we have to write the necessary equations. But before we do so, it's advising us that we should really simplify this circuit, because the only types of simplification available here are single node pair or single loop, which means basically we should be able to get this into one of those two forms. And if you look at the problem, we say, well, if we can combine those in series and then combine the resultant in parallel here, that will make it single loop. So we go into the circuit editor to do that job. So the first thing we have to do is we recognize that these two elements are in series, and now because we're in the phasor domain where everything is in ohms, we can in fact just add those impedances. So here I could just go minus J 11.11, and notice that's now in red. What does that mean? Well, the label down here tells us that means that the entered impedance is not consistent with the current element type, and that element type might need to be changed. So in fact, that's a fully complex number which is not compatible with a resistor. A resistor must have a real impedance, and a fully complex value is not suitable for a resistor. So we're going to change the type of element to a generalized impedance, which is allowed to have a fully complex value. And notice that the red error message went away. And then this element, well, it wouldn't make any sense, of course, to delete this element. That would or change it to an open circuit, because then this wouldn't be connected to anything and it wouldn't be equivalent to the original circuit. It would just be dangling. So for sure, when we're in series, we change these to a short circuit. So I'll click on that. And now we'll check that combination. And that is correct. And now we have to combine these two impedances in parallel. Now what about the sought voltage? Will that affect this? Well, remember that sought voltage actually appears across both of these elements. Since they're connected in parallel, they both have the same voltage. Therefore, combining these two impedances will not affect that sought voltage, and that is a legal operation. If this had a sought current, that would be a different story, and we would have to convert it into a sought voltage before we could combine them. But here we don't need to do that. So in order to combine those two impedances in parallel, I will need to use a calculator. So let's go back to the calculator. And now we have to remember that when you combine impedances in parallel, we need to take the reciprocal of the sum of the reciprocals of the individual impedances. So I'm going to enter here 1 divided by open parenthesis for the denominator. And then I'm going to have 1 divided by the J7.2, and since that's a product, I'm going to use parentheses there, and we'll make it I 7.2. Close that parenthesis, so that completes the first reciprocal, and then we add to that the reciprocal of the second item, so that's 1 divided by, and we could perhaps also use the reciprocal key, but I'm just using it this way. And open parenthesis there, and I'm going to have 2 minus I 11.11. Close that parenthesis for that reciprocal, and then another close parenthesis to close the denominator. And that should be correct now. I can go back if I like and review the expression to make sure it's all correct, but it does appear to be. So now I'll click enter, and that gives me the total impedance. And notice that I did put this in rectangular mode so that I would have it. If I forgot to put it in rectangular mode, then I could just go change the mode now and then re-enter this expression and evaluate it so it would come out in the rectangular mode as desired. Or I could use a math function that would convert it, but this is the easier way. So, okay, so now I'm going to go, and to avoid having to move this sought voltage, I'm going to enter this value directly here. So that will be 5.375 plus J17, 17.71. And notice also that's in red because, again, that's not appropriate for an inductor. An inductor should have a positive imaginary impedance, and this is a fully complex number. Therefore, we have to change that. And so I'm going to click on the general impedance symbol, change that element to that. And then the red lettering goes away, which means that that's now acceptable. And because I'm combining these two elements, now I need to change this one to an open circuit. If I changed it to a short, for example, of course, that would short everything, and that would be equivalent to not having had any elements there in the first place. So that certainly wouldn't make any sense. So I delete that element. I click the delete key or the delete key on the keyboard, or I could have right-clicked and deleted it. Also, when you right-click on an element, you do have the option to delete it down here. So there's several ways to do that. Okay, so now we're going to check that combination. And that is correct. And now I'm going to go back full screen here. And we're done with the circuit editor. So I'm going to click Done Editing. And now I am single loop, so that means that I can use a voltage divider formula since I have a single voltage source and two impedances. So I'm going to select single loop analysis. I don't have a single node pair, so I couldn't use that. And it'll just give me an error if I try to do that. And then I'm going to come down here and select the SOT branch voltage, since that's what I want to compute, the V0 value. And that shows me appropriate terms for doing that. So V0 equals, and now I'm going to use the simple voltage divider formula for two impedances, which is this. And now I need to put in the value of the source, which is 4 angle 0 degrees. 4 angle 0. And then I'm going to multiply that times the impedance of interest, which is Z1. So up here I'm going to put 5.38 plus J 17.7. Oops, typed the wrong thing there. So that should be plus J. And then I can just copy that, save retyping it, and put it down here in the denominator. And then the other impedance is just 3 ohms. Now, remember that I use the impedance of interest because the voltage source divided by the sum of all the impedances in the loop will give us the current in that loop. And multiplying the current times the impedance of interest will give the voltage across that impedance of interest, the Z1 impedance. Therefore, that's what makes sense. Now, before I try to check that, though, I want to be very careful about checking polarity. So notice that the positive side of this voltage source is actually connected to the negative side of the SOT voltage, and the negative side of the source is connected to the positive side of the SOT voltage. So those have opposite senses, and therefore this would not be correct as written. I need to have a negative sign out front. So I could either put a negative sign there, or I could change the 0 to 180 degree phase angle, because remember, 180 degree phase shift is equivalent to multiplying a complex number by -1, since -1 in polar form is simply one angle 180 degrees, which you can see if you look at the argon diagram as indicated in the tutorial. I don't want to do both of those things, of course. That would then not make any change. So I'll just put the negative sign there. Let's check that equation. So that is correct. And so now I've written all the equations I need. I just need the one. So I click No More Equations. And now it tells me I have to enter a numerical value for this, which I will have to compute with my calculator. So let's go back to the calculator. And so now I'm going to put a -4. -4 angle 0 degrees is simply like -4. So I put -4. Times, and now I'll put my numerator in parentheses, and that will be that 5.38 plus this. And so to do that accurately, I'm just going to actually go up there and grab that number, and then close parentheses. And then this will be divided by an open parenthesis for the denominator. And I want to go back up and grab that number again. And then that number has to be added to 3, so I'll put +3. Close the parenthesis for the denominator. And I'll just go and review just to make sure that everything looks correct there before I click Enter. And I believe it is. So now we'll just click Enter. And this time I had forgotten to put it into the polar mode, so now we have that value coming out in rectangular form. And for this form, I need it in polar mode. So I'm going to go back and change modes now. And go down here to the mode and go over to polar form and go enter there. And now I can just go back up and grab the expression I had done before and re-enter it. And now it appears in polar form as I need it. So now I'll enter that here as 3.779 angle negative 171.6 using 4 significant digits for accuracy. And let's check that number. And that is correct. And now the last step is going to be to convert the voltage in the phasor domain back to the time domain. In other words, I have to do what's called an inverse phasor transform, which is very simple. And that means that I need to write it as a cosine function. So the magnitude in front of the cosine function will be the magnitude of the phasor. That's just going to be the 3.78 here. And then the quantity that multiplies t is always omega, so that's our angular time frequency, which is 90 radians per second. Now, if that were, for example, 90 kiloradians per second, I would write it out as 90,000 here because it will not accept a metric prefix in this field. So I just write pure numbers. In this case, it's just 90. And then the phase angle is this minus 172 degrees, so I put minus 172. And notice these are always in degrees, not in radians. And that is correct. And that completes the problem. And I can get a more detailed solution, or explanation rather, by clicking there. And then that will explain a little bit more how this worked. So that completes this problem.